Hi everyone, welcome back. My name is Mika Wan. I'm a second-year doctoral student at Carolina Health Informatics program in Biomedical Health Informatics. My research interests are mainly in natural language processing, text summarization, and graph theory. In this module, we'll be talking about bivariate analysis. As you might have guessed from the title, bivariate analysis deals with the relationship between two variables. For example, cholesterol and blood pressure, or head and weight. Bivariate analysis helps us to find other variables which move in concert with the variable we are interested in. Surely, with 3 or more variables, we have multivariate distribution, but they are not in the scope of this class. There are 2 different perspectives that you will need to pay attention. The first concerns to the strength of the linear relationship between the 2 variables, which we call correlational approach. In this relationship, neither variable is said to depend on the other, and the other is regression model, which talks about how one variable varies as a function of the other. In this second case, we will examine whether one variable is dependent on the other variable. In this module, we'll be focusing on the correlational approach, which means we will be examining 2 variables that are not necessarily dependent on each other. For example, when you look at this chart of the total US highway fertility rate and the fresh lemons imported to the US from Mexico, you may see that these 2 variables are correlated, that when the amount of lemon imported from Mexico increases, the total US highway fertility rate decreases. If you admit that these two variables are in the relationship of causation, you also admit that Mexico lemons are somehow killing the Americans on the road. However, unless the lemon from Mexico is some superpower fruit that can leverage its magic on US highway or US vehicles, we won't be able to claim that the US highway fertility rate is dependent on the imported lemon. That's what we call correlation does not equal to causation. Let's talk a little bit about significance level before we dig into the relation types. In determining the relation of 2 variables, we need a value to decide whether the relationship between 2 variables are statistically significant or not. In other words, the computed result needs a measure of trust to determine if it is statistically significant. In most of the cases, we use a p-value. A conventional threshold is 0.05. That is to say, when a p-value is less than 0.05, we say the result is significant. The p-value roughly indicates the probability of an uncorrelated system to produce a dataset that have a correlation at least as extreme as the one computed. That is to say, the smaller the p-value is, the unlikely your result is found by an accident. Officially, we assume a null hypothesis at the very beginning, which assumes that there is no relationship between the 2 variables you are investigating. Then we calculate the p-value according to the test you use for examining the relationship. The lower the p-value, the more confident you are to reject the null hypothesis. We will continue with variable type in the next section. Now let's take a look at one question first.